Today we're going to extend our studies to physical pendula. When we talked about regular pendula, we just talked about a ball on the end of a string. But now we use our knowledge about the center of mass, which is actually in the middle if this is a rotating rod. Let's see what this can do through an example. But first, a couple things we need to remember. First off, if you have a moment of inertia, to find the total moment of inertia from your system, just add up all the components around whatever axis you're looking at. The second piece is the parallel axis theorem, which says that your center of mass moment of inertia plus the mass of that object times the distance squared that it is from the rotation, from the center of mass to your new rotation point, equals your new moment of inertia. So let's take a look at what we can do with this. And the example we're going to consider is just a clock bob from like a grandfather clock. I'm just going to use variables because it makes things a little easier to follow. And we want to find the angular frequency, so we're looking for omega. Now, the important place to start in any harmonic oscillator equation is the equation for a harmonic oscillator, which is the second derivative of function is negative some constant squared times the first function. And the reason this works is because the solution to this equation, you can use a sine function, you could use a cosine function, you can also use exponentials, but we'll just stick with sines and cosines, and these oscillate back and forth. So always start right here. Now in this case, instead of linear position, we're going to do angular position, which is theta, and where you know that d squared theta dt is alpha, your angular acceleration. Oh wait, now we need acceleration. So how do we find accelerations? Well, same way we've been doing them in this class. With energy. So with energy, we'll start by writing the energy equation. Now in this case, if this were to spin in a complete circle, our center of mass wouldn't be moving. So we're not going to worry about kinetic. Gravity, yeah, gravity's going to act on this. No springs, so we can take those out. Then we're going to use our things that we've talked about. By things, I mean, of course, moment of inertias. So this is the superposition of the moment of inertia for the bob and this rod right here. And the shift is because this is the center of mass. So we have to use parallel axis theorem. These are just your gravitational potential energies. No big surprise there. So let's look at the eyes first. This is a rod rotating about the end. Then we have a disk, but that disk is shifted by this much for its center mass. So we use parallel axis. And I'm just going to write this as eye system because if you carry all those letters, it gets really hard to see what you're doing. So here we are, I system omega mg. Now we have thetas, we don't have y's. So let's compare this. And I can find that our y center of mass for the rod and the disk are related to the cosine of the angle theta. So we'll plug this in, I'll put these numbers in, substitute for y, that's the proper term. Okay, then we'll combine like terms. Now we need to find the angular acceleration. So to do this, we'll take the derivative with respect to position of that whole thing. Well, it's an isolated system, so we get a 0 on this side. We're going to use our old tricks. Derivative of cosine is negative sine, so that's why that plus popped over. And then this dividing right here, where d omega d theta is actually d omega dt, dt, d theta. Break it up into parts and chain rule. And you'll find that this omega and that omega cancel, this 2, that 2, divide out to 1. And you're left with just alpha. Good so far. So now I can get alpha equals g sine theta, but let's use our small angle approximation. Sine theta becomes theta. Then we can solve. And look, now I've got alpha, the second derivative of angular position, is negative some constant times your original angular position. Now from before, I know that that constant is omega squared. So I'll just write omega right here. Omega squared. Then we'll get back, instead of I system, remember we had this nasty, not really nasty, just this expression that we derived before. And it's a little longer, which is why I wrote it as I system when carried out. It's a good trick. And then take the square root of it. And that's your answer. And that is how you find the period of oscillation, or the angular frequency, sorry. You can get period, because period is just 2 pi over omega of a physical pendula. Same type of thing. The key difference is you now have I of the system, which you need to worry about, and then you have to take your force from the center of mass instead. So if you have questions, please ask, and I will see you in class.